Hello everyone. So previously we had discussed on the topic this one Prim's algorithm, right? So today we'll be discussing on the topic disjoint set union, also known as union find, right? So basically used for the path compression, right? So let's get into the definition part here. Disjoint set union, also we call this one as DSU. It's a data structure used to efficiently manage a collection of disjoint sets, right? So we know this. So let me tell you this one again. Let me read this one out loud again. So disjoint set union DSU is a data structure used to efficiently manage a collection of disjoint sets, right? Supporting union and find operations. What does it support? It supports one is union and another one is find operations, right? So these two operations are supported by the DSU. One is union as well as the another one is find, right? The path compression, what it does, it optimizes the find operation. So we have two operations that is supported by the this one disjoint set union. One is union and find operation. So here path compression optimizes the find, the second one, find operation by flattening the structure of the tree, making future queries faster, making the future queries faster. So that's what the path compression does here, right? So let's get into the explanation part, man. Let's go with the DSU basics first. So DSU disjoint set union, what it does, it maintains sets where each set has a representative, where each set has a representative in the sense parent. Each set will be having certain parent, right? So also known as representative here. So find of x, this one, find of x, what it does, it returns the representative or the parent of the set containing x. What it does, again, it returns the representative or the parent of the set containing x. So this is for the find operation. So what is union of x comma y here? This one. So this merges the sets containing x and y. So we'll be having two sets, right? So it merges the sets containing the values x and y here. Union of x comma y. Find of x, what does it do? It returns the representative or the parent of the set containing the x, right? So let's move on with the next step here. Nothing but the path compression. So now we have the idea on the basics, right? Idea of the this one. Basically, we went with the basics of the DSU, right? So now let's move on with the path compression step here. So path compression, while finding the parent of the element, see here, it this one within the find of x, it returns the parent of the set containing the x, right? So we need to find, basically we are finding the parent, right? So while finding the parent of an element, we update the parent of every visited node to the point directly to the root, right? So there will be something called root, right? There will be root basically, right? Primarily there consists of, it consists of the root basically, right? So while finding the parent of an element, we update the parent of every visited node to point directly to the root, right? So this reduces the tree height and makes the subsequent find operations nearly constant time, makes the subsequent find operation nearly constant time. So this is related to the find basically, where we return the parent or the this one representative of the set, right? So containing x basically. Now what are the use cases of the this one DSU, right? So DSU is widely used in the algorithms involving connectivity like crystals, right? So it is widely used in the algorithms involving connectivity, right? Like crystals. So previously we had discussed crystals and the Prim's algorithm, right? So mainly DSU is widely used in the algorithms involving connectivity, where we had made use of the DSU itself, right? If you remember. Yeah. Now the second one is minimum spanning tree. The same thing. DSU is widely used in the algorithms involving connectivity like crystals, minimum spanning tree, then detecting cycles in the graph. This is also one of the this thing main advantage or the use case of the DSU, right? For detecting the cycles in the graph and the network connectivity queries. These three things: crystals, minimum spanning tree, detecting cycles in the graph, and the network connectivity queries. These are some of the test cases I wanted to discuss with you guys, right? So this is fine, man. Now, as we have the idea how it works, right? So let's start writing the code or the let's move on with the algorithm basically, right? So with the help of a Python programming language. So let's do one thing. Let's go with the disjoint set union with a path compression, right? First, let's initialize the DSU. So I'll just go with the class DSU here. This is fine. First, let's go with the this one initialization or the constructor part. So this will be in it. So let me remove this. I'll just go with uh, n along with the self, right? So this is fine, man. First, let's go with the parent of y. So parent of I here, it will be the point to the parent of I, right? So initially each element is its own parent. That's what I want to say. So this one will be parent equals, let me initialize this one with I for I in range actually. Yeah, I, yeah, I for I in range of, let me pass n here. Yep, this is fine, man. Now let's do one thing. I'll just go with self dot initially I'll just go with the rank and let me go with 0 into n. This is fine. Yeah. Oh, why this is screaming here? Expected expression. So this is correct itself, right? Uh, in it we are going with the initialization part. So this is fine. Self and n I have made use of. Self dot parent we are going with. This one I have assigned with I for, yeah, this one has to be I, man, not for I, this one, I for I in range, right? So this is fine. Now, let's do one thing. Let's move on with the, we have to go with the two helper methods, right? Or the two methods or the functions, basically. One will be going with the find as well as the union, accordingly with the explanation, right? Part that we discussed. Recently, we had discussed the explanation part where we discussed that we'll be making use of two things. We have to go with the find as well as we have to go with the union, right? Find of x and union of x and y. So first, let's go with the find method. So this find, what we will be finding here, accordingly with the explanation, we should be able to find the representative of the set containing x, representative also known as parent, right? So I'll just go with the def here, find, let me go with self and x. Simple, yeah. We should be able to find the parent of the x, right? In simple terms, representative of the set containing x. So here, if parent, yeah, parent of x, if it is not equal to x, then what we will do, then we have to go with the path compression. Path compression in the sense, we will be going with the recursion. Just remember this, path compression will be going with the recursion. Recursion in the sense, we will be recursively finding the root and we will set the parent of x to it. So that's what we'll be doing with within the path compression, right? So I'll just go with here, parent of x. So let me assign this one to the find of this one, parent of x, right? So this is fine. Now let me return something here. Return parent, right? So this is fine. Parent of x, right? So this is fine. Now let's do one thing. Let's go with a this one union method. Now we are done with the find method. So let's go with the union method or the union function. Union, why? We have to find the union, or we have to go with the union of the sets containing x and y as per the explanation, right? So this one will be def union of self, this one x comma y. So this is fine. Yeah. Now let's find the roots of x and y. So this one will be x root equals find of x. This is fine. Equals, oh, so this one will be y. Yeah. Now this is fine. What if x root and this one y root we consider, right? What if x root is equivalent to the y root? Then what we need to do, then they are already in the same set and we have to exit from there. So I'll just go, sorry, let me give colon here, forgot this one. Yeah, let me give return here. This is fine. Next step here would be we have to go with a union by rank. So that is the reason we have considered rank here within the initialization part, right? So we have to go with the union by rank, nothing but we have to attach smaller tree under the root of taller tree. So this one we had made use of this one within the Kruskal's algorithm, if you remember, or if you can just go and check that video as well. I had said this one. So we will be going with a union by rank, nothing but we will be attaching the smaller tree under the root of this one taller tree. I had explained certain things there itself, right? So Yeah, let's do that. Basically, let's attach the smaller tree under the root of the taller tree, or in simple terms, let's go with union by rank. So I'll just go with a simple if condition here. Rank of this one. Let me go with the x root. If it is less than this one, rank of this one, what do we call y root? Yeah. Now let's do one thing. I'll just go with parent of we have to consider x root. Actually, parent of x root. Let's assign this one to the y root, because we are attaching the smaller tree under the root of this one taller tree. Right. Let's go with the what happened here. Sorry. Let me go with the elif or the else if elif, right? So as we are making use of the Python, so this one will be rank x root. So if it is what if it is greater than this one, rank of y root. So I should have copy pasted and made the necessary changes one instead of typing. This is fine. Let me go with the y root. So then let's put parent. So this one, let me copy this one. Let me paste this one. So I'll put parent of this one y root. Let me assign this one to the x root. Simple. Yeah. Now, yep. Next thing is let's go with the else. Let's go with the else, right? So if ranks are same, then make one root and increase its rank. So this one will be self dot parent of y root. So this one y root. So let me assign this one to the x root. So this is fine. Self dot rank uh, this one of x root. We'll just go with this one rank of x root plus 1 finally, right? So we are done with this department. This is just by we just went with union by rank. This is simple. So we are done with the DSU algorithm. So this is it for the algo. Very simple one, man. So let me paste the example usage basically. So we are done with the algorithm. I hope I have explained everything step by step here. So we went with only two methods. One is find and another one is union. Within the find, what we are doing, so in the explanation part I have said that we will be finding the representative or the parent of the set containing x. That's what we did, right? So within the find we went with a path compression, nothing but we recursively we are or we had recursively found the root and we had set the parent of x to it, right? So that's what we did in the find. And what about the union? So we went with the this one union of the sets containing x and y. Basically we should be find or we had found the roots of x and y, and also we went by union by rank, meaning we attached smaller tree under the root of taller tree. That's what we did within the union. Now let's go with the example usage. Just give me a second here. So I have just pasted this one, right? Example usage. So what we are doing here, DSU equals DSU of 5. So we are just creating the DSU with the 5 elements. What are the 5 elements here? 0, 1, see here, 0, 1, 2, 3, 4. 5 elements, right? So just give me a second. Let me show this one. We are considering 0, 1, 2, 3, 4. These are the 5 elements. We went with basically. We just created the DSU with the 5 elements 0, 1, 2, 3, 4. This is fine. Now DSU of union 0, 1, 1, 2 and this one 3, 4. We are just making use of the union method here, right? The class DSU along with this one, we are just going with the union. DSU is this one a variable, sorry. And this one union, we are making use of the helper method union here. So we are merging the sets containing 0 and 1 here for this one 0, 1, and we are merging the sets containing 1 and 2 in this case. Here in this case, we are merging the sets containing 3 and 4. This is simple, very simple. Next, we have made use of the print just for the interactive purpose here. We are just going with the parent array after the unions, right? So we are just calling here parent. This one, see here, dsu dot parent. This is fine. So this one are 0 and 2 connected. So this one, what is this basically? We are checking if 0 and 2 are in the same set or not, right? If they are in the same set, then only 0 and 2 are connected, right? So that is the reason we are going with a find here. We are going with a find a dsu dot find of 0 and dsu dot find of 2. So we are checking whether if 0 and 2 are in the same set or not, right? So R0 and 2 connected, so that is the reason I have written like this. Next, we are going with R0 and 4 connected. So we are checking if 0 and 4 are in the this one same set or not this time again. So we are making use of the DSU.find of 0, DSU.find of 4. So what is the output that we need to get here accordingly with the this one? What do we call the example that we considered basically? So let me delete this one now. I hope this part is completely clear, man. We are going with basically 0, 1, 1, 2, and 3, 4, right? 0, 1, 1, 2, and 3, 4. The parent array after the unions would be, so this one, 0, 0, triple 0, 3, and 3. So this is the this one, what do we call, the parent array after the unions actually, right? Are 0 and 2 connected here? Are 0 and 2 connected? So basically if they are in the same parent array, we are checking, right? So if they are in the same this one set, sorry, if they are in the same set, we are considering here, are 0 and 2 connected? Yes, 0 and 2 are connected. We have to get the output true. And are 0 and 4 connected? 0 and 4 are not connected, so this one we have to get false here, right? So this one, I believe this is clear. If you didn't get it, let me explain you. So the parent array after the union triple zero double three, how we got this one? So 0 is the root of the first segment. Yeah, see here, 0 is the root of the first set. Yeah, we are considering the elements 0, 5 elements, right? So this one 0, 1, 2, 3, 4. Listen to this carefully if you didn't understand. So 0, 1, 2, 3, 4. 0 is the root of the first set, right? So this one will be split into half. So this one will be 0, 1, 2, right? Disjoint set union. This one will be first set. 0 is the root of the first set, 0, 1, 2. So 1 and 2 point to the 0. So 1 and point to 0. So this one I can just write it in this way. 0 is the root, 1 and 2 will be the children. So this points 1 and 2 point to the 0, right? 1 and 2 point to the 0 here, right? So this is fine, I believe, right? So 0 is the root of the first set, 0, 1, 2. So 1 and 2 point to the 0 after path compression. After the path compression, 1 and 2 point to the 0. I hope this is clear. And 3 is the root of, 3 is the root of the second set, 3, 4. This one. We have another one, 3, 4. We are left with two elements, right? Split into half. So this one 0, 1, 2, and 3, 4. So this one 3, 4, 3 is the root of the second set, 3, 4 here. So this one 3, and we can just write the 4 in this way, right? 4 points to 3 basically. 3 is the root of the second set, 3, 4, and so 4 points to the 3 here after the path compression, right? 4 points to the 3, right? So parent, so this one, parent array after the union would be, so this one, 0, this one, this 1 and 2 also points to the this one 0 itself, right? 0, the root, the parent one we are considering, because in the find this one method, so we are going with the this one, what do we call, find. What we need to find here, basically we have to find the this one representative of the set, right? Representative of the set. So this one for 1 and 2 points to 0. So this one, the parent is 0 itself, right? Among 0, 1, 2, the first half that we considered. So we have considered 3 zeros here. And what about 2, 2, 3 we got here? Twice 3. So 4 is pointing to the 3 after the path compression. So this is the root actually. This is the parent. 3 is the parent of this one 4. So we are having two elements. We will be writing 3, 3 here. That is how we got this one, the output triple zero double three. So this one I have said, right? Triple zero double three. If you didn't understand, I went this one, I elaborated. If people like me exist, right? So we don't understand the things at the first time itself, usually, right? Sometimes we understand first time itself. Some other time we don't understand. We have to this one go in detail, right? We have to learn in detail, then only we understand certain things, right? So this is how we got this one, triple zero double three. This is fine. Now are 0 and 2 connected? Yeah, 0 and 2 is connected. Both 0 and 2 have the same representative 0. See here, both 0 and 2 have the same representative 0 here, this one, right? So this one, 0, same representative 0. So they belong to the same set here. So they belong to the same set, the first of this one, right? So here in this case, it has to be true. This one true, right? So this is correct, right? So then we are checking whether 0 and 4 are connected to the this one. Are 0 and 4 are connected? So here see, For this half, we have only 0, 1, 2. This part we are considering 0, 1, 2. And 4 is at the other half, man. 4 is not at all linked to 0. This is not linked to 0 at all, this one, right? So this is not linked to 0 at all in this case, right? So they don't belong to the same set. They don't belong to the different this one, the same set basically. Different roots means they are not they are in the different set. So 4 is having the root 3 and 2 is having the 1 and 2 are having the root 0, right? 4 doesn't belong to the root 0 here. So 4 and 0 and 4 are not connected. In that case, we have to return Boolean value false, right? So this is the reason we'll get the output 000 followed by true and false. I hope the solution part is completely clear, man. Now, yeah, whatever the example usage we have considered, I hope this part is clear along with the algorithm, whatever I have explained. This is one of the simplest algorithms, man. Yeah, fine. I hope this is clear, man. Now, let's do one thing. As we have the idea on the algo and the example usage, let me run the code. I'll just come here. Let me copy this one. I'll just give Control J here. This is fine. Python followed by file name.py. Uh, syntax error. Line number 30. And, not equal to x. Line number 30, 30, 30. So within the find, so what mistake we have done here? If I have written, okay, self parent of x. Yeah, this is correct. Parent of x. Not, oh yeah, I have given semicolon here. So let me remove the semicolon. Now this has to be correct, I believe. So let me give clear screen. If it is not equal to x, so this has to be colon actually, not the semicolon, right? If condition we are writing here. So let me run this one again. Yeah, now we are getting the correct answer, right? So see here, 000 followed by 33, which I explained. We have got the desired output, right? For this one, parent array after union. And are 0 and 2 connected? Yes, 0 and 2 are connected. So we are getting the output true. So this is also fine. Next, are 0 and 4 connected? So 0 and 4 are not connected because 4 doesn't belong to the root 0. It belongs to the root 3. First, we'll split into half, right? It belongs to the root 3. In this case, no, it is not connected. We have to get the Boolean value, output Boolean value false. Basically, we are getting the Boolean value false. So the output, we are getting the desired output, or we are getting the expected output here in this case. So whatever the algorithm we have written works absolutely correct, right? So this is fine, man. Now we are done with the disjoint set union, also known as union find, right? Union find or disjoint set union DSU for the path compression, right? Or using path compression, right? So this is fine, I believe. One of the simplest algorithms, man, right? So now let's do one thing. Let me summarize whatever we have learned so far. Just try to remember these 3 to 4 points, right? So the first point here would be DSU efficiently manages dynamic connectivity among the disjoint sets. What it does, it efficiently manages dynamic connectivity among the disjoint sets. This is one of the important things. And so we have discussed this one. The second point, the path compression ensures find operations are this one nearly big of one average, right? So nearly big of one on average, right? So again, this is very important. So path compression, we will be going with, or we went with a path compression because this is extremely fast, man. Path compression ensures find operations are nearly big of one on average, right? So basically, we make use of the DSU whenever in the, whether if you are giving contest or whether if the problems are based on the graphs, if you are making use of the DSU, so you are going with the extreme optimization, whether it may be in lead code, whether it may be this one, code chef, or the this one, code forces or the code chef, anything it may be. So usually we make use of the disjoint set union, this one, for the extreme optimization or the intense optimization itself, right? So I hope this part is clear. Path compression ensures find operations are nearly big of one on average. And so we went with the union by rank as well, within the this one, union helper method. If you remember, union by rank further optimizes the union, preventing the tall trees. So that's what we did, right? If you remember, I said while writing the union method, so I said one thing. So we went with the union by rank just to make sure that we are attaching the smaller trees under the root of taller trees, right? So we are attaching the smaller trees under the root of the taller trees, right? So here again, union of rank further optimizes the union, preventing the tall trees, right? So now DSU, so the fourth point or the final point here, DSU is backbone for many graph algorithms like Kruskal's, this one, minimum spanning tree, and the cycle detection. So again, I said, so previously, before this one, we discussed Prim's and the Kruskal's algorithm. So while discussing the Kruskal's algorithm, we have made use of, or we had made use of uh, this one itself, disjoint set union itself, right? So if you would have watched that video, if you wouldn't, if you haven't watched that video, you can just go and watch that video as well. If you have the idea on the Kruskal's algorithm, it's fine. If you don't have the idea, then you can just go and watch this one, the video Kruskal's algorithm, right? So there we have made use of the this one, disjoint set union or the union find algorithm, right? So DSU is the backbone for many graph algorithms like Kruskal's minimum spanning tree and the cycle detection. So this is it for the this one, disjoint set union algorithm. Right. So I hope the algo is completely clear, man. Right. Next, what we'll do? Next, we'll be discussing on the Tarjan's algorithm. Right. Tarjan's algorithm. For now, this is it. Thanks for watching, guys.